Hello there, and welcome to our lesson today. So, this next chapter that we're going to be getting into is um, all about what's called transcendental functions. And I know when you're going through school and you don't hear that word too much, but basically, a transcendental function is just a non algebraic function, not a polynomial. All the stuff that we've worked with so far have been polynomials throughout calculus. Well, a transcendental function is your log functions, your exponential functions, your inverse trig functions, basically all the other stuff is what this chapter is about. And I don't like to do a lot of memorization stuff. I really like to talk about concepts, but the transcendental stuff is, a lot of memorizing derivative rules and integration rules and things like that. So we're just going to dive right in. So today's lesson, we're going to be talking about how to find the derivative of a natural log function. We haven't talked about that. We're going to talk about integrating with natural logs. And then we're going to talk about e to the x. How do we differentiate and integrate e to the x? There's a lot of stuff in this lesson. I'm just going to forewarn you about that. I'm not going to do every example on the notes, so it looks like there's a lot, but we're not going to do all the examples. And then through your practice, hopefully, a lot of issues get taken care of. So let's start. So we want to find the derivative of the natural log of x. Pretty easy derivative rule. If I want to find the derivative of the natural log of x, all it is, 1 over x. The derivative of the natural log of x is 1 over x. And again, that's just something you're going to have to remember. Oftentimes, there's going to be a function inside the natural log. So we call that u. Like u is a function of x. It's the same rule, except now we have to apply chain rule because we have an inside function as well. So if we want to find the derivative of the natural log of u being some function of x, well, it's 1 over u times u prime. So it's 1 over the thing inside the log times the derivative of what's inside the log. A lot of times you'll see that rule written as u prime over u. So it's the derivative of the inside over the inside is what that rule is. Again, you just have to remember it. So if I want to find the derivative of natural log of x squared plus 1, then it's the derivative of what's on the inside. So the derivative of the inside is 2x over what's on the inside, x squared plus 1. So the natural log goes away. It's the derivative of the inside over the inside. Or you could do 1 over the inside times the derivative, because that's what you're doing is chain rule there. Let's do one more here. So we can write the natural log of square root of x plus 1 as natural log of x plus 1 to the 1/2, right here. You have a couple of options. I guess the easiest thing to do, now that I'm looking at it, this is different than what's on my key. Remember, a log property says if you have an exponent inside of a log, you could pull that exponent out in front. So I can actually write this as 1/2 natural log of x plus 1. This is not what I did on my key. I just saw this now. And now it's going to be, if I want to find the derivative, remember we always label. We don't just write like equals and then do the derivative stuff. We have to label the derivative. It's going to be 1/2 times whatever the derivative of this is. Well, the derivative of natural log of x plus 1, it's going to be the derivative of the inside. So 1 over the inside, which you could just write as 1 over 2 times x plus 1. There it is. We'll skip 3 for right now. So that's the derivative of natural log. It's u prime over u. And now what we're going to do is integrate. So we're going to kind of go in both directions in this chapter. So if the derivative of the natural log of x is 1 over x, we know that. We just talked about that. If that's true, then if I would, look at what would happen. If I would integrate both sides like this, if I would integrate both sides, then the integral and the derivative over here would cancel out, and I basically get the integral of 1 over x is the natural log of x. We're going backwards. If you remember, we had power rules for everything except x to the negative first. Like if I asked you guys to integrate 1 over x squared, we could write that as x to the negative second, and then do our power rule. Increase that by 1 and divide by it. We know that. And when we did this at the time, I said it works every time except if your exponent is -1. If that's the case, you can't use your power rule because then you would increase that to 0 and then divide by 0, and you can't divide by 0. So this is now, for the first time, us integrating 1 over x, or x to the negative first power. Okay? So here's our rule. If we are going to integrate 1 over x with respect to x, then we can't do the power rule. This is the only one we can't do the power rule on, but we're going to get the natural log of the absolute value of x, that's something you're going to have to remember, plus c. Again, here's our next rule. The reason we have to put the absolute value on, and you're going to have to remember to put the absolute value on, is because you can't take the log of a negative number. So we put the absolute value here to account for that. You can't take the natural log of like -4. So that deals with that issue right there. So the integral of 1 over x is natural log of absolute value of x plus c. There's going to be a lot of u substitution that you're going to see. We're going to do some examples here. When we get into natural log integration like this, it's rare you're just going to be integrating 1 over x. You're going to be integrating like 1 over 2x plus 1, 1 over x minus 8. You're going to be integrating things that it's not just 1 over x, and if that's the case, then it's u substitution. So we're just going to do some examples on the back. But bottom line, to use this rule, you need to either get 1 over x or 1 over u. You have to get your integrals in this form to be able to use this rule. So let's look. So I have the integral of 1 over 6x plus 1. It seems like it would be so easy to look at this and just say, oh, don't write this. Natural log of absolute value of 6x plus 1. It's just natural log of whatever the denominator is. And it's not the case. Because it's not in the form of 1 over x or 1 over u, we have to put it in that form. Okay? So I mentioned when I went over the homework with u substitution how oftentimes if you have a fraction, you're going to have your denominator be your u. And that's what's going to happen here as well. So we're going to have u equal 6x plus 1. We're just going to go through our normal u substitution procedure. So then du equals 6 dx. And then I always pause here and I look, what am I trying to replace? Well, 6x plus 1, so that got me 1 over u. And then I'm trying to replace dx. Well, I have 6 dx. So divide both sides by 6. And then I can come over, and remember that number in front of the du just goes in front of your integral sign. And then it's 1 over u du. And now I can integrate because I have it in the right form. So my integration rule is, if I'm integrating 1 over u, it's the natural log of the absolute value of u plus c. And then I just replace 6x plus 1 where the u is. There it is. I talked in the homework the other day how if you have that like linear term in your function with u substitution, all that's going to happen is you're going to get that reciprocal of that coefficient out in front. You notice you get that same answer we thought we might, but then you get that 1/6 out in front. And so for some of you, maybe you can take that little shortcut. I don't advise it, but it is something that you could do. Okay. Example 5. And then we'll talk about e to the x. So this one's a definite integral. And, I talked about how do you know what to have u stand for, and I've said, well, pick u to be something where its derivative shows up somewhere else. And if I have u be x squared plus 1, its derivative is 2x, emphasis on the x right here, which shows up in the numerator. So that tells us that we're going to have u substitution here with x squared plus 1. So du equals 2x dx. I'm trying to replace x dx. Well, I have 2x dx, so divide by 2. And then I come over, and I have 1/2 the integral. And now it's going to be 1 over u du. And remember, when you're doing definite integration, you never have to go back to the x's. I would always encourage you to change your limits of integration from x values to be u values. And remember how to do that. If I put 0, if 0 is my x value here, then u is going to be 1. So my corresponding u limit is 1. And if x is 3, I put it into this equation here. 3 squared plus 1 is 10. So my upper limit is 10. Now I never have to go back to the x's. So now we integrate. It's going to be 1/2. And then the integral of 1 over u is natural log absolute value of u from 1 to 10. And then plug in 10. Plug in 1. With logs, you are going to have to remember some properties. You know, with trig and with logs, that is oftentimes where I find the most mistakes made, where students get the right answer, but then pick the wrong multiple choice answer. Like they know the calculus, they know how to do it all, but then can't do the manipulation. That happens with trig and with logs. So if this was a free response question, you could leave this answer because it's all numeric and you're done. But if it's multiple choice, you probably have to clean this up. So we need to think, do I know what the natural log of 10 is? Well, no. Remember with logs, this is saying e to what power gives you 10, and I don't know. But here, I know what natural log of 1 is. Remember, this is saying e to what exponent gives you 1. This is 0. If you take the log of 1 ever, it becomes 0. So natural log of 1 is just 0. That whole thing is gone. So you have 1/2 natural log of 10. That might be the choice. But they also might write their choice as natural log of square root of 10. Maybe that's the multiple choice answer that you'll see on the paper. Maybe you get this, but that's the answer, because maybe they took the 1/2 and put it up as a power. 10 to the 1/2 is the square root of 10. So just with manipulation and logs, this is one where you guys are doing your assignment. I would try to get to the back of the book answer just to work on your manipulation skills, because there's nothing more frustrating than doing a problem right and then not being able to find the answer choice. So that happens with logs. So that's all with natural logs that we're going to talk about. How to differentiate. It's just the derivative of the inside over the inside. And then with integrating, you're just integrating 1 over u or 1 over x. Where students then run into issues is this. If I ask you guys now what happens to integrate this, I get so many students that think now anytime I have a fraction, it's just natural log of the denominator. Or they'll look at this and try to do u substitution, but it's not going to work because the derivative of x squared is 2x, and there's no x up here. This is just a prime case where you would rewrite it and then use your normal power rule. So once you learn more integration tactics, it does get harder because you have to know what to do when. And that just comes with doing more and more problems. So be careful with that. Okay, I saved the easier stuff for second. E to the x. So just like we talked about finding the derivative of natural log of x, let's talk about the derivative of e to the x. And this one's really cool, and it's really nice. The derivative of e to the x is just e to the x. It's itself. It's one of the only functions where if you differentiate it, it becomes the exact same thing. I think 0 might be the only other one. If you take the derivative of 0, you get 0. If you take the derivative of e to the x, you get e to the x. It's pretty awesome. a lot of times e is going to be raised to a function of x, so all that happens is chain rule. So if we want to find the derivative of e to the u, it's e to the u, it's exactly what you see, and then times the derivative of u, times the derivative of the inside of that exponent. So that the e one is really nice. So if I want to find the derivative of e to the 2x minus 1, it's exactly as you see it. It's e to the 2x minus 1. But then you have to multiply by the derivative of the exponent. So times 2. Let's put the 2 out in front right here. And usually that's the biggest issue, is people forget to multiply by the derivative of the exponent. It's pretty straightforward with e. Do one more here. First thing I would do is rewrite this as e to the negative 3x to the negative first, because that way when we find the derivative and stuff, we have our powers and everything. So my derivative is going to be exactly as you see it, times the derivative of the exponent. So remember how to find the derivative, multiply the exponent to the negative 3, so 3, and then reduce the power by 1. Right there. Alrighty, we're going to skip 3 and 4. Let's talk about integrating. Well, again, just like the derivative of e to the x is e to the x, if you integrate e to the x, you get back to e to the x plus c. Don't forget about plus c. There will be some u substitution, because if you look at the examples, obviously it's not just e to the x. I mean, it could be, but most likely it won't be. It's going to be e to some power, which means there's going to be u substitution involved. So if we integrate e to the u, we get e to the u plus c. So if you're integrating e, you're going to choose the exponent to be your u, okay? So this one right here, we want to integrate e to the 3x plus 1. So we're going to have u equal 3x plus 1. So that's going to give us e to the u, which is what we want. But now we have to get rid of the dx. So du equals 3 dx. We're trying to replace the dx, so divide by 3. And then you get 1/3 the integral of e to the u du. And the integral of e to the u is just e to the u. It's exactly as you see it. And don't forget plus c. And then you just plug in 3x plus 1 back for the u. There it is. It's probably good enough. So you guys have an assignment, and like I said, it's just a lot of practice and rule memorization. When you're integrating, there's a lot of u substitution. When you're finding derivatives, oftentimes a lot of chain rule. So good luck on your homework. Peace.